You step onto the surface. 1 second. That is all you get before everything you are made of ceases to exist in any recognizable form. Not because of heat, not because of cold, because of a force so extreme that the atoms inside your body, every carbon atom, every oxygen atom, every electron that holds your cells together, would be compressed out of existence before you could exhale. Welcome to a neutron star. What you are standing on is the corpse of a sun. A star between 8 and 20 times the mass of your own sun finished burning, and in a fraction of a second, its iron core, the size of Earth, collapsed inward under its own gravity. The collapse took less than a quarter of a second. What remained was an object roughly 20 kilometers across. 20 kilometers, less than the distance between two cities. And yet packed inside that sphere is more mass than your entire sun. This is not a metaphor. This is measured. Astronomers Jocelyn Bell Burnell and Anthony Hewish first detected signals from these objects in 1967, rhythmic radio pulses so precise and regular that the team initially called them LGM-1, Little Green Men, because they could not believe a natural object could be so clockwork. They were. The object was spinning and emitting radiation beams like a lighthouse. What they had found was a pulsar, a rotating neutron star. The universe had built something more precise than any clock human beings had ever constructed. Now imagine you are on its surface. The gravity you feel on Earth is 1g, a unit of force that your body evolved over millions of years to live inside comfortably. On a neutron star, the surface gravity is approximately 200 billion g. 200 billion. If you weigh 65 kilograms on Earth, on this surface you would weigh about 13 trillion kilograms. The number is meaningless in human terms, so let us translate it differently. A marshmallow dropped from 1 meter above the neutron star's surface would hit with the energy of a nuclear weapon. Your entire body, standing on that surface, would be flattened to a layer thinner than an atom in a fraction of a millisecond. But you would not even reach the surface. Here is what would happen first. As you approach, tidal forces begin tearing at you. Tidal forces are not exotic. They are the same principle that makes ocean tides on Earth. The gravity pulling on the side of your body closest to an object is slightly stronger than the gravity pulling on the side farthest away. On Earth, the difference across your body is negligible. Approaching a neutron star, that difference becomes catastrophic. The near side of your body would be pulled billions of times harder than the far side. You would be stretched lengthwise and compressed from the sides simultaneously, a process physicists call spaghettification, though the term undersells the brutality of what happens. Every bond holding your molecules together would be overcome. You would not be torn apart. You would be atomized, unmade at the level of individual particles, long before your feet touched anything solid. Still, science asks us to imagine. So let us keep going. If your body somehow survived the approach, if you were made of something far stronger than matter as we know it, you would step onto a surface that looks, in some simulations, like a crystalline metallic shell. Beneath that crust, pressure increases to a point where our physics begins to fail us. Neutrons, the particles at the core of every atom you have ever touched, are normally held apart from each other by quantum rules. A neutron star crushes matter past those rules. Electrons and protons are forced together until they merge into neutrons. The interior of the star becomes a sea of neutrons packed at nuclear density, the same density as the nucleus of an atom, but sustained across an object the size of a city. At the very center, some models suggest the matter becomes something we do not have a confirmed name for: quark matter, hyperons, or states of matter so exotic that no laboratory on Earth has ever produced them, even for a fraction of a second. We genuinely do not know what is at the center of a neutron star. Our physics is incomplete. What we do know is the temperature. A newly formed neutron star burns at approximately 100 billion degrees Kelvin in its core, hotter than a supernova, hotter than anything in the current universe except the moments immediately following the Big Bang. The surface temperature, even after thousands of years of cooling, hovers around 1 million degrees. Compare that to the surface of your sun, about 5,500 degrees. The neutron star's surface is nearly 200 times hotter than your sun's outer layer. And the surface is radiating in X-rays, not visible light, X-rays, the same radiation type used in medical imaging, but concentrated to a flux so intense that it would ionize every atom in your body before any other effect had a chance to act. Astrophysicist Robert Duncan and Christopher Thompson studied the most extreme version of neutron stars in 1992, objects called magnetars, and described magnetic fields a quadrillion times stronger than Earth's. Quadrillion. These fields are so intense they distort the shape of atoms themselves, compressing electron orbitals into elongated cylinders aligned with the magnetic field. Matter cannot exist in familiar forms anywhere near a magnetar. The chemistry that holds you together would simply stop working. You would not die. You would unbecome. There is a counterintuitive truth buried in all of this. People assume the most dangerous thing about a neutron star is the temperature, that you would be burned. Or they assume it is the radiation. But the physics says something stranger. The first thing that would actually destroy you before heat, before radiation, is the magnetic field. If you were approaching a typical neutron star, not even a magnetar, the field intensity would disrupt the electrochemical signals in your neurons before any other mechanism had time to register. Your thoughts would stop. Your heart would stop. Every electrical signal in your nervous system would be overridden by an external magnetic force of roughly 100 million Tesla. Earth's magnetic field is about 50 microtesla. The field of the most powerful MRI machine humans have built is about 45 Tesla. 100 million Tesla would end your cognition instantaneously, before the gravity crushed you, before the X-rays ionized you, before tidal forces stretched you. You would not experience this. There would be no sensation, no pain, no last thought. The electromagnetic processes that produce consciousness would simply switch off, in the same way a screen goes dark when power is cut. And yet, neutron stars are not destroying things. They are some of the most stable structures in the universe. Pulsars, rotating neutron stars, keep time with an accuracy that rivals atomic clocks. Some have been spinning for billions of years without measurable slowdown. J0437-4715, one of the most precisely timed pulsars known, rotates 174 times per second and has been doing so for so long that astronomers use it to detect gravitational waves, ripples in spacetime, by watching for tiny disruptions in its otherwise perfect clockwork rhythm. That object, that city-sized sphere of compressed death, is one of the most reliable timekeepers in the observable universe. Look up tonight. The sky you see is not dangerous. The light touching your eyes traveled for years, some of it for millions of years, and arrived carrying no more energy than your retina can comfortably absorb. You live in a protected bubble, a planetary magnetic field, an atmosphere, a distance from your nearest star precisely right for liquid water and life. The universe allows these quiet pockets, but it also builds neutron stars, objects 20 kilometers wide that contain more mass than a sun. Objects that spin hundreds of times per second and emit radiation that would disassemble you before you could name what was happening. Objects so dense that a sugar cube volume of their matter would weigh 100 million tons on your kitchen scale. The universe has two modes. The one you live inside, and everything else. You step onto the surface. 1 second. That is all you get. And in the fraction of that second before unbecoming, here is the last physics lesson the universe offers you for free. The rules that govern your body, chemistry, biology, the electromagnetic force holding atoms together, are not universal laws. They are a local convenience, a lucky exception that happens to exist in one thin shell of habitable space around one ordinary star. Out there, other rules apply, and they are far less forgiving.